Good morning students, my name is Professor Padhi. Today I am going to teach you digital electronics. So today I will discuss about comparator. It's a 2-bit comparator. So what does mean by comparator? Means it will compare between two binary numbers. Suppose it is given it is 2-bit number. Suppose a number is A, that is denoted as A1, A0, that means 2 bits. Similarly, suppose another number is there, that is B, B1, B0. So now we have to compare between these two numbers. Okay. So first, when we are going to compare between numbers, there may be 3 possible cases. One is either A will be greater than B. This is the first condition. Second condition will be either A less than B. These are the 2 conditions. Another condition is both numbers will be same. So these are the 3 conditions when we are comparing between 2 numbers. These 3 conditions will arise. Okay. So first of all, this is A greater than B, that is denoted as G. A less than B, that is denoted as L. A equals to B, that is denoted as E. So one by one I will discuss it. Okay. So first condition is what? Greater than B. So let us consider 2-bit number A equals to A1 A0, B equals to B1 B0. So now tell me, when the condition will satisfy A greater than B, that means A1 must be either 1 and B1 must be 0. That means this bit will be 1, this bit will be 0. Then the condition will satisfy that A greater than B. Or if both the numbers or both the bits are same, suppose A1 equals to B1, that is also possible. A1 equals to B1, that means we will go for the next bit. A0 will be 1 and B0 will be 0. So either this condition will, if this condition will be satisfied, then A equals A greater than B, or if both the bits are same, A1 equals to B1, then we will go for the next bit, A0 B0. That means A0 will be 1 and B0 will be 0. So this is the condition when A greater than B. Now for this A greater than B, what will be the expression? What will be the expression? The expression is denoted as G. First condition, A1 equals to 1 and B1 equals to 0. That means A1, it is denoted as AND, means AND gate. A1 is 1, that means A1, B1 is 0, that means that is B1 complement. Okay? OR gate means there will be a plus symbol. A1 equals to B1. In the truth table, when the 2 bits are equal, which gate will satisfy this condition? XNOR gate. That means A1 XNOR B1 AND gate means into A0 is 1, so A0 and again B0 is 0 here, so that means B0 bar. So this is the overall expression when A greater than B will be satisfied. So this is the expression for A greater than B. So now we will go for the next condition, A less than B. Similarly, you tell what will be the value for A less than B. There are 2 bits, A1 must be 0 and B1 must be 1. That means this bit will be 0, this bit will be 1. Then condition will be satisfied that A less than B. Another, if A1 equals to B1, if these 2 bits are equal, then what we will do? We will go for the next bit. Next bit is AND. So next bit will be, this value will be 0 because it is less. This value will be 1 because this is this value will be 1. Sorry, this value will be 1 because A greater than B. So A1 value will be 0 and B0 value will be 1. If this is 0 and this is 1. So A less than B will be satisfied. So this condition will be satisfied. So now, what will be the expression? You tell me, what will be the expression? This condition is denoted as L for less than. So L is equal to A1 is 0. That means A1 bar, and means and get symbol into B1 is 1. That's when B1. Similarly, OR get plus A1 equals to B1. That means A1 XNOR B1. Then A0 is 0. That means A0 bar into B0. So this is the expression for A less than B. Okay. So now the third condition is A equals to B. So what will you tell? What will be the expression for A less than B? So A equals to B. A equals to B means both the bits will be same. This bit will be equal to this bit, and this bit will also equal to this bit. Then only we can say that A equals to B. Both bits are equal. Either this value will be 1, this value will be 1, this value is 0, this value is 0. Similarly, this value, if this value is 1, this value must be 1. This value is 0 means this value is 0. So when this condition will be satisfied, that way will be denoted as E for equals. So A1 must be equals to B1 and A0 must be equal to B0. So these two conditions will be satisfied. So now tell me what will be the expression? E for A1 equals to B1 means A1 XNOR B1 and get means into A0 XNOR B0. So this is the equation for equals. So we got the three expressions. Now we can draw the two circuit diagram accordingly. So hope you will understand it better. So in the previous section we have studied about 2-bit comparator. Now we will study 3-bit comparator. Suppose there are two numbers, one is M, another is N. Suppose there are two numbers, digital numbers, binary numbers, M and N. It is 3-bit, that means you tell that is M2, M1, M0. There are 3 bits. Similarly, N will be denoted as N2 and N0. Now we will compare between these two numbers. So what are the possible conditions? N must be, M is either greater than N, M is then M can be less than N, or M can be equals to N. So there are 3 conditions. M greater than N, that is denoted as G. Then second condition, M less than N, that is denoted as L. Third condition, M equals to N, that is denoted as E. So there are 3 conditions. Now I will explain you bit by bit. Okay, first condition is, now the first condition is M greater than N. So how it is possible? M2 must be 1 and N2 must be 0. If this bit is 1, this bit is 0, obviously M is greater than N. Suppose M2 is equals to N, or if M2 equals to N2, then if the 2 bits are equal, then we will check the next bit. That means the next immediate bit M1 and N1. So M1 must be 1 and N1 must be 0. Then only we can say that M is greater than N. If these 2 bits are equals to these 2 bits, M2 is equals to N2, M1 is also equals to N1, then we will go for the last bit, M0. What is the condition? Or if M2 equals to N2 and M1 equals to N1, then we will go for M0 must be equal to 1, M0 must be equal to 1, N0 must be equal to 0. So if these conditions are satisfied, then we will say that M is greater than N. So M0 is 1 and N0 is 0. So what is the expression? What is the expression for G? First condition, M2 N2 bar, then plus M2 X naught N2 into M1 N1 bar. Last condition is M2 X naught N2 M1 X naught N1 and last M0 N0 bar. So this is the overall expression. This is the overall expression for m greater than n. If m greater than n, for m greater than n, this is the overall expression. Similarly, for m, you can do by yourself. M less than n, for m less than n, second condition, n will be equals to just reverse m2 bar n2 plus m2 x naught n2 m1 bar n1. Last condition is m2 x naught n2 m1 x naught n1 m0 bar n1 n0. So this is the expression for L. So now the third condition, last condition, m equals to n. For m equals to n, all the three bits will be equal. So that means for E, for the value of E, m2 x naught into m1 x naught n1 and m0 x naught n0. So this is the overall expression for a 3-bit comparator. This is for m greater than n for G. This is for m less than n, that means M, and this is m equals to n, that is equals to E. So this I hope you have studied comparator very well. If you have